All right, ladies and gentlemen, let us start. Oh, I don't show anything. How come? Yep, that works. So, today is the last lecture of quantum transport, and we've been talking for quite a while about quantum phenomena in electron transport, in qubits, but we didn't discuss at large mechanisms and phenomena which actually spoil quantum mechanics, making the behavior of quantum particles, qubits, more classical. And today, in the last lecture, we finally have a closer look at this phenomena. I will talk about dissipation. We know what is this. It's an energy dissipation, particle loses energy. Decoherence and dissipation, roughly it is the same. It happens that if we talk about qubits, we frequently call it decoherence, while for electrons, which just fly in the metal, it's rather called dephasing. So what is the plan for today? First of all, I look at all this phenomena from classical point of view, although it's not really the subject of quantum transport, but that will give us a good introduction into the phenomena. We will learn something interesting, I hope. Then we do a bit of technicalities. We will understand how decoherence and dissipation comes in quantum mechanical description. We will look at the environment which we need for this phenomena, the models of this environment. Then the story will evolve. First of all, we will talk about qubits. About dissipation and decoherence, about nasty environments which can completely localize the qubit, make it quantum. Then we talk about electrons at large. And I will finish with some classical experiments on dephasing and relaxation of electrons in metals, which partially gave you results which you could predict and partially gave something unexpected by that time. And that would be it with the content of quantum transport. I believe that next Tuesday, if not mistaken, there will be yet another session on homework. And then I will see you next time on the exam. Actually, I don't remember when we have the exam. Is it somewhere like 1st of July or earlier? What, 23rd of June? Okay, this year everything goes faster, perhaps. Perhaps the Earth goes faster. Right, good. Let us talk about classical mechanics. We understand that Newton mechanics, which we learn at school and which seem to be the base of scientific understanding of everything, eventually quite idealized set of concepts, because it heavily relies on energy conservation and time reversibility. So all Newton equations can be reverted in time, and that is not what we see in real world. In the real world, we have friction, energy loss from any given degree of freedom, and the microscopic origin is clear. All degrees of freedom in this universe are coupled, either weakly or strongly, and even weak coupling would cause energy loss, friction. Right. What is the usual example? The usual example is damped oscillator. Right. If the ideal Newton mechanical oscillator, while excited, would keep the amplitude of oscillations forever, while real oscillator will lose it. And that happens, attention, at some time scale, 2D. Right? Time scales will be important in our story. So that's how one can characterize dissipation. The longer the time is, the less dissipation we have. Right, that's all clear. Less usual story is about a classical decoherence, a classical dephasing. It doesn't appear in all courses in physics, which I guess a bit of pity. Perhaps you have heard it, but let me just cite something trivial about this. Let us see. Suppose we have some realistic oscillating system, which ideally, like an ideal oscillator, would keep its phase and amplitude. Eventually, for many systems, there's no problem to stabilize amplitude. Well, you just supply energy to the system, you keep amplitude at the same level. It is more difficult to stabilize the phase. Classical problem is a problem of mechanical clocks, or whatever, electronic clocks. So what is going on in clocks? There is some driven oscillator which is supposed to work at frequency omega naught. But in fact, the frequency depends on plenty of parameters which fluctuate a little bit. It depends slowly, it depends weakly. The change of parameters is small. Nevertheless, whatever parameters, pressure, temperature, and so on, there are fluctuations of these parameters. And although these fluctuations are much smaller than omega, the fluctuation of phase will eventually grow in time. It's the first side, it seems kind of unusual, right? So parameter is small. Why don't fluctuation of phase stays at the same small level? Nor the phase accumulates. It's the integral of this frequency. And if you average this, fluctuation of phase will increase linearly with time. That's somehow illustrated by this plot, where I show two oscillations with a very small difference in frequency, And we see that the phase difference between these oscillations just increases in time and approaches big values. Fine. This is decoherence, classical decoherence, whatever. It is also characterized by time, phi. Right. What I want to say. Right. You can say that phi is a time when this fluctuation will become of the order of 2 pi. One can quantify it a little bit better. And right, suppose we look at some characteristics of our oscillator displacement, and this is at constant amplitude would be just cosine of phase. If you look at the correlator of these two, we can represent it as exponents, just rewriting exponents in the cosine. We can average over the phase, right? And what we found here is exponent minus phase fluctuation. This increases linearly with time, as we know from here. So that correlator will be exponential function of time. Where do I write it? So also in this case, the dephasing or decoherence is characterized with a time scale. Let us see. I wanna tell you something which is also decoherence and which is also relevant but different. I wonder, it becomes very rare today. I wonder if you ever visited shop where they sell mechanical clocks that really ticks, right? Then you do remember the sound in this shop. It's very unusual because all these clocks, actually they keep their frequency very precisely, but the frequencies differ by a small bit. Somewhere at second range, in your second range, and that gives rise to very strange and sometimes very harmonic random pattern of this, right? So it's a sum of many coherent oscillations, but since the frequencies of these oscillations differ a bit, it is still a manifestation of the coherence, in fact, right? So I just put here signals of different frequencies. You might want to sum them, and if you sum them, yeah, you would have something which goes like this, which decays. So it's called apparent decay. So it is not really decay of anything. Amplitude doesn't go down. It's not even dephasing of each individual clock. It just because we listen to many clocks simultaneously. To some extent, it's our problem. It's a problem of what we observe. Right, so it also can be characterized by tau phi, and this tau phi can be just estimated by uncertainty in this frequency. Good. That was classical mechanics. It demonstrates already a variety of decoherence mechanisms. All right, let me go to quantum transport and let us understand what dissipation and decoherence means uh, in quantum mechanical framework. Dissipation is energy loss, but in quantum mechanics, it is specific that it can only occur in the form of transitions between different quantum states. Right. The spectrum of the states can be discrete, like in the case of qubits. It could be continuous, like for electrons in a metal. Right, they complete electronic states completely fill the energy window. It's continuous spectrum, and decoherence or dephasing again. It's basically the same in our context. Is of a very specific phase, the phase which we have in quantum mechanics. Right, the phase of the wave function. Right. That decoherence can occur between discrete states, like in a qubit. Qubits all have finite relaxation time. Finite decoherence time. One can see, for instance, why if you apply a signal with frequency which matches the energy, resonant manipulation, we talk about this. Then the signal from a qubit will decay at some scale, manifesting its decoherence of Rabi oscillations. That are states of different energy, but there could be the decoherence can break interference between electronic waves at the same energy, like for instance in Aronoff bomb effect, there are two electronic passes, that one, and the electrons propagate just at the same energy. Still, interference will be broken by decoherence. Good, sir. In quantum transport, the manifestations are also various, but you have to put it into quantum mechanical framework. Dephasing, destruction of quantum interference, dissipation, transition between quantum states. Having that in mind, could you please explain me a universal relation? I bet it's universal, which I put here. We are talking about two time scales: dissipation, energy loss, and decoherence, disappearance of coherence, decay of phase, one can say. So why this relation is valid? It is something which you can deduce from information and this transparency. Perhaps it's so simple that you don't want to deduce. Why the coherence is decoherence time is shorter than dissipation time. Okay, let me argue as follows. For coherence, we need at least two quantum states, right? If dissipation happens, we go, for instance, from excited to the ground state. So we don't have two states, we have one. So you cannot keep a phase coherent for a time which is longer than dissipation time. Transitions with energy loss will kill the effect. Right, so the opposite situation can occur. One can have these two states, but the coherence can be lost. That can happen. So that explains this relation. Fine. Let me go a little bit technical. It's not that much of technicalities, but let me sort out how would you describe this phenomena in a quantum mechanical description. I just looked, put very general one without much details. Let us see. First of all, we need to understand that to describe a decoherence and dephasing in some system, and that system has states labeled by n. We need other degrees of freedom. We need plenty of other degrees of freedom. Okay, that I put here. So that's gonna be environment. Okay, that's our system, that's environment. And I need interaction. What does it mean? Interaction, coupling between these two systems. It implies that Hamiltonian has matrix elements which mix different states. If it just mix different ends, would it work as dissipation decoherence? No, it won't. That would go to the system Hamiltonian. If it mixes some k states that also don't count, it changes this Hamiltonian. But there are elements which are responsible for dissipation and decoherence. For instance, this is non-diagonal element, and thereby a system from state n prime could go to the state n. Simultaneously, the state of environment can change. Good. How about decoherence? We want to look at the phase of the same state, right? And in this case, we don't want to change it, right? If we change, it would be dissipation, it would be transition. The point is that transitions can be in environment. So environment changes while the state of the system does not. There are also matrix elements like this, and those are responsible for decoherence. In fact, one can see it, and we will put it rather explicitly, one can see it as energy difference fluctuations, like in a clock, fluctuations of frequency, because energy in quantum mechanics is the same as frequency. Okay, let me make a concrete model for a qubit. It is in two states. And let us see, first of all, I put it as energy difference. coherence. Good, so I have two states, plus and minus. The matrix elements corresponding to the states, everything is diagonal. Fine, what is the coefficient? Coefficient contains some constant term, splitting, plus some fluctuations. Right. These fluctuations I can represent as some bosons of environment of the bus. That's one term. I want to think of other term, which is non-diagonal. Look here, you go from minus to plus, from plus to minus, and there's also some field which energizes these fluctuations. Just for simplicity, I will reuse the same field. Just put it here, the same field, but with some coefficient A, which can be anything. It can be very slow dissipation, as we have noticed. Right, so how to characterize these fluctuations? Well, as usual, as a classical quantity, we can also do it for quantum quantities. We can characterize the fluctuations with a spectral density of its noise. Okay, defined as a square root of Fourier, average square root of Fourier component of this noise. What I want to use, which is valid for any system, it is a relation between, it kind of gives us temperature dependence of the noise at any frequency. So temperature dependence goes here to this factor, and here we have a noise at zero temperature, quantum noise, which means that if temperature is 0, it just becomes 1. Otherwise, in opposite limit, it becomes kBT divided by h omega. It's proportional to temperature. It's thermal noise. Good. So let us look with this model on the dissipation and decoherence. How do we assess dissipation? Well, we just compute, we just imagine that, for instance, it is simple to assume that qubit in the high state, say plus, then what happens is a transition to another state with emission of a single boson to the environment. Good. One can compute it by Fermi-Golden rule. One gets it, and let's see what we have at energy at zero temperature. Okay, so some coefficient, intensity of coupling. What I want to say is that this is sensitive to the spectrum of the fluctuations at very certain frequency, at the frequency of the splitting. To some extent, it's natural. The fluctuations which cause transitions must be in resonance with the level splitting. Fine. Finite temperature, if temperature is finite, we can utilize this formula and understand their transitions upwards, downwards. Their intensity is given by Bose-Einstein distribution, because we are dealing with bosons, and writes at any finite temperature, we will find thermodynamic equilibrium as a consequence of transitions upwards and downwards. There will be a finite probability to be in both states, which is just given by Boltzmann factor, does not depend on the environment. Fine, that was dissipation of the qubit. Let me think of decoherence. It's a bit complex, but after all, it is simple. Just let us concentrate. To understand decoherence, let me first consider a very simple case. The fluctuating field is classical. How could it be? We have, for instance, a qubit. We want to manipulate it. We want to change something with a qubit. To this end, we kind of have a control channel. We vary some quantity, qubit changes. But one cannot open a channel without opening it for noise of this variable. So there will be always classical fluctuations of these, let's call it energy splitting. Good. So what would be the reaction of the qubit on this? Okay, the phase is just integral of energy difference. So the fluctuation of phase, yeah, it's just given by integral of these fluctuations. Okay. And let us assume white noise. So the frequency fluctuations are correlated like this, kind of instant fluctuation, instant correlations without delay. The fluctuations at two given moments of time do not depend on each other. Right. Then we get to this. Now we have a fork. I can tell you more how to get to this formula. Or you can say, you know how to deal with that. It's not very quantum. It could be part of some other course. It's your choice. Make your choice. Are you satisfied with this formula? Do you find it kind of sufficiently? Are you sufficiently confident about this formula, or you want some derivation?
I can't quite see how it's derived. I can't quite see how it's derived, so you could explain it briefly.
Okay, let's see. Perhaps I still have a all transparency with derivation. Good. A bit clumsy, right? But let me. So this is definition of phase difference, which is accumulated from 0 to time moment t. Here integration is over t prime. Fine. Let me just write the squared. We can add signs of averages later. Okay, that's what I have. So since I'm writing the squared, I have integral from 0 to t from two variables, t prime, t2 primes. And now I have corresponding fluctuations. Now I average. So what does it mean? If I'm working with a white noise, I want to replace this with delta function of time difference. Fine. So I have two integrations and one delta function. This, shall I write it explicitly or is it okay? Okay, let me write it explicitly. Good. So I can kill one integration by using delta function. So let me complete integration over t with over t with two primes. Good. Then I just have constant.
I don't quite understand how you get from the, how you get to use the delta function. Why do you use delta function?
Delta function comes from the property of noise, right? Before the average, you just have two fluctuation variables, right? And you have expression for delta phi. If you average, you need to replace these two epsilons with a correlator. Yep. Correlator is a delta function, which means that fluctuations at separate times do not correlate, but yeah, there's fluctuation correlates with itself. Fine. So we have integration. We have delta function here. We integrate it over one variable. Another variable remains, and this integral is t. Right. So we have proved that this fluctuation grows with time. Fine. That allows us to define decoherence time when this quantity becomes of the order of 1. So here we are. Let us look at it. Inverse decoherence time is proportional to the intensity of that noise, white noise at zero frequency. Oh, fine. Now I wanna tell you some quantitative qualitative trick which perhaps will help you. I find it very, very, how can I say, instructive beyond things which we study. First of all, let me talk about the following. Let me understand which frequencies in fluctuations are responsible for formation of decoherence time. If you think about the answer, is a bit tricky. Those frequencies which have the same scale as decoherence time. Okay, let us assume for a while that decoherence time is sufficiently long, smaller than temperature in frequency units. In this case, we could disregard frequency dependence of the fluctuations, provided noise takes some finite value at zero frequency. That justifies white noise approximation. Okay, so we have this formula for white noise. Okay, we can compare it with dissipation, which is at pretty different frequency, at the frequency of splitting. Now let us understand that environments, noises, can be very different. And it doesn't have to be to go to constant at zero frequency. It could be kind of colored environment. No, the noise doesn't have to be white. So how we can modify this formula to get the coherence time in this situation? Okay, we write what the coherence time is, and we take noise at frequencies of the order of the coherence time. So instead of answer, this relation becomes an equation. An equation for tau f, and that brings us to classification of possible environments. We look at thermal fluctuations only because frequencies are low anyhow, and then at low frequencies, noise is just proportional to temperature, and we have some power of characterizing spectrum of the noise. It's power law at low frequencies. And there are different cases. First of all, the noise can rise at low frequencies. S would be smaller than 1. In this case, we have eventually danger, a problem at sufficiently low temperatures. Why is it so? Because 1 over tau f is this power of temperature, and at sufficiently low temperatures, we don't satisfy these relations anymore. So fluctuations become quantum, and something strange should happen with our qubit in this range. I can tell you what is this something strange. Qubit loses the coherence completely. It becomes a classical memory cell. It can be in 2 states without any transitions between them. Good. Ohmic, it's wise noise. We know that. And 1 over tau phi is proportional to temperature. And there are super ohmic cases. And in this case, we have finite coherence time, which grows fast with temperature. And even if this S parameter, for instance, it could be noise proportional to V squared. Then, funny enough, the coherence is incomplete. The system subject to such noise remembers the initial value of the phase. That's it. This is classification of the environments. So the answers can be very different. In any case, at low temperatures, the coherence is a power law of the temperature, but okay, this power law varies. Fine. I think it's time for a break. Let's have our traditional 8 minutes break. Go on with the story. Good. So, classification of the environments, the decoherence can be tricky if the environment is colored, but in any case, it's a power law of temperature. Right, what do I have here? Right, so a little bit about subomic regime. If you followed the course of advanced quantum mechanics, I've been talking quite a bit about this in the last lecture. In subomic regime, the environment eventually destroys the quantum works of the qubit. It is not delocalized anymore. The qubit really consists of two separate states. There is no overlap between the states. If it is on the left, you cannot find it on the right, in distinction from quantum bit, from qubit, which really obeys quantum mechanics. So subomic kills quantum mechanical properties, and all right, that yeah.
What is the regime that we find ourselves in most?
What is the most usual regime? Eventually, it is ohmic. In almost all systems which are affected by electricity, noise comes from resistors, and it's usually white noise. All right, so ohmic is very widespread regime. We will see other examples when we talk about decoherence in the metals. But this ohmic is just a borderline between subohmic and superohmic, and here it's good for quantum mechanics. Here it's pretty bad. Fine. Then let us look a little bit at manifestations. Some simple but interesting things to understand. Dissipation. Let me take our old system consisting of two barriers, double junction. I will take it sufficiently big with many channels, so I can talk about electron distribution not only in the lids but also inside between these two barriers. All right, and what would be this distribution? So here plot field factor at horizontal axis versus energy. What would be this distribution? If there's no energy loss, and what does it mean? Of course, electrons which transfer nanostructure will lose energy sooner or later, right? But if this happens when they have already passed the nanostructure, you don't see it in the transport. You don't care that they lose their energy. So they don't have to lose energy when they are in the nanostructure, when they dwell TW, time which they spell in nanostructure. Right? So if the dissipation time is much longer than the time of being in the nanostructure, we can talk about elastic transport. And what is the manifestation? In the field factor, in the middle, we have two steps. instead of 1 in the leads. Why is it 2? Because it is connected to both leads. Fine. What happens if there is dissipation inside the nanostructure? Okay, then electrons have time to collide with each other. They exchange their energy. Dissipation takes place. This condition. Okay, but this energy doesn't go away from nanostructure. It is accumulated. What does it mean? It means that there will be enhanced temperature. And right, in this regime we have just instead of two steps, we just have featureless spread of the distribution function. What happens if we manage to evacuate the energy from this nanostructure? Okay, if we do it consequently, the distribution just becomes the same distribution at 0 temperature. So we will have a step again, but only a single step instead of 2 steps here. And the position of the single step will be somewhere in between the positions of the step and the leads. So that's a manifestation of dissipation in electronic distribution in nanostructures. What would be manifestations of dephasing, again for electrons? Let us suppose at the moment that the electrons lose the coherence at some time scale. So phi. You can immediately convert it to length scale. That will depend whether electrons propagate ballistically or they scatter in the structure. It's more usual case. If they diffuse, here's the relation. It's just the length at which they will diffuse during time tau f. Okay, let us look at some nanostructure when we expect interference. Let us, for instance, make a Aronov-Bohm ring. We remember that when we have interference of trajectories with different windings around the loop, we will have conductance which depends on the flux in the loop. Aronov-Bohm effect. Okay, would it survive? Would it survive coherence? No, it's all about the phase of the wave function. If the phase of these two passes is affected differently, the coherence will be lost. So there will be no magnetic field dependence of the transport. When does it happen? One needs to compare the size of the structure with this scale. Scale comes from time, but you can express it in terms of length if you know how electrons move. Right. Another manifestation, another interference effect which we looked at, weak localization. Small interference contribution which survives after averaging over the samples. Right. In this context, we've been talking about the sequence of coherent conductors. So long macroscopic sample is not coherent, but one can separate it into coherent pieces. Well, size of this piece again is given by this length scale. Right, so we can eventually figure out how many coherent conductors are there in our sample and estimate weak localization accordingly. What else? Yeah, we can recall that there are two space scales related to the interference. Magnetic field gives different fluxes to different trajectories, and thereby it also cancels interference at some scale at which the trajectory picks up a flux of the order of flux quantum. Right. Now, if we measure, for instance, conductance trace versus magnetic field, we see transition between coherent effect and incoherent, and the width of this transition in magnetic field eventually characterizes the decoherence. Transition from weak localization disappears at magnetic scale of the order of this length. This is practical way to characterize the coherence time. In most measurements, at least I'm aware of, they extract the coherence time from magnetoconductance. Fine, that's manifestations. Let me talk about mechanisms. First of all, mechanisms of dissipation. In normal world, at room temperature, and even at temperatures which are like hydrogen at temperatures which are very cold, the dissipation of electrons in metals is dominated by phonons. Why is it so? Because any electrons in metals are necessary in crystal lattice, and the oscillations of this crystal lattice provide a natural environment for these electrons. Right, there are always bosons which are coupled to the electrons. Interesting feature which reveals lots of different physics is that dissipation due to phonons goes down very quickly with decreasing temperature. Okay, one can estimate it from intensity of states of the photons that this scales as a cube of energy, and energy involved is of the order of temperature. So, in fact, this dissipation time becomes irrelevant below 1K. You also see it from experimental case. Okay, what happens, which mechanism will become dominant at lower temperatures? It's again electron interaction. So instead of interaction with phonons, electrons can interact with each other. I want to in order to explain these estimations which I put here, I want you to recall that electrons interact by means of electricity. So, in fact, what fluctuations which other electrons produce in a given electron are electromagnetic field, electric field fluctuations. Let's keep it simple, electric. From the other hand, the fluctuations of electric field in a medium are given by resistance of this medium, right? That's why the dissipation eventually depends on the relevant resistance of the structure. Okay. But what is the relevant resistance? It's again a kind of bootstrap, which we have seen today when we wanted to figure out decoherence. It is the resistance, which is the resistance of the sample at some space scale. What could be space scale? In this case, we are talking about energy losses, which are the Rodorf temperature. And from this, we can make space scale. Now let us consider the samples of different geometry. We can consider a metallic wire, a metallic film, or just take a three-dimensional piece of metal. And let us see how resistance depends on the scales. It will grow in quasi-one-dimensional system. The resistance will be proportional to the length. For a film, it would hardly depend on the size. For a film, that resistance and that resistance are eventually the same. And in 3D, yeah, one can say this, it will be inversely proportional to the length. That sets different temperature dependencies of dissipation in different geometries. Interesting, observable effect. People had lots of fun with this. Okay, that was about dissipation. Let us talk about mechanisms of dephasing. Eventually, any mechanism which provides dissipation could be also used for dephasing, although there are mechanisms which are specific for dephasing, which don't do much for dissipation. So let me list it. Again, phonons can dephase. It's relevant at low temperature. Electron-electron interactions. And right, it's very interesting to see that decoherence, in this case, is completely determined by classical Nyquist noise in the metals. In fact, one can even say it measures it. And it will depend on geometry, more or less because of the same scenario. Nyquist noise is determined by resistance, and resistance scales differently with lengths at the same at different geometries. Besides, there are spin effects. Well, because spin of an electron is, in fact, a sort of the phase, two-component wave function. If you have, you can rotate it also in spin space. It's also a kind of phase. Right, so there are mechanisms which involve spin orbit scattering, and we know that they change interference at some scale, but it doesn't kill it completely. There are, however, spin effects which affect interference, which kill interference, which lead to decoherence. For instance, the electron spins can scatter at stray magnetic impurities. Say, for instance, take a clean metal like gold. Anyway, you could find there some amount of impurities of magnetic metals, for instance, iron. Right, that could be 1 per million of atoms, but that can cause sufficient scattering for electrons moving at the scale. Good, those are mechanisms. Let me talk about Nyquist noise. I find it very instructive and easy to comprehend. First of all, let me remind you the following. I wonder if you know this formula or whatever heard about this. Somebody should have told you, I'm pretty sure. What does it mean? It gives you time-dependent fluctuations of a voltage on a resistor in the limit of low frequencies, we can regard it as a white noise. These fluctuations are proportional to temperature, but also to the resistance. They are, it's not an independent parameter. They are really bound to actual resistance of the sample. It's called fluctuation dissipation theorem, whatever, but yeah, usually in electronics it goes without mentioning such fancy names. Just voltage fluctuations are proportional to resistance. So how does it affect phase? Well, we just need to integrate fluctuating voltage over time, as we did. Again, we square this phase difference to compute the average. We have the answer, which is proportional to time. And resistance comes here, temperature comes here. Here we are. Good. Let me look at what we have. We have inverse decoherence time. It is compared with the temperature in frequency units. And we know it is good when decoherence is smaller than temperature, otherwise it gets quantum. It becomes, it signals something strange going on. So it has to be smaller. And what is a small factor? Small factor is the resistance which produces noise in units of conductance quantum. So our old acquaintance comes again into play. Right, now one has to understand which resistance plays the role. If the resistance, it is the resistance of the sample on the scale. So in fact, like we saw recently in decoherence, this is not an answer, it's an equation from which one should determine this decoherence time scale. Let's do it. Interesting answer is for one-dimensional y. I will also show how it is realized in experiments. And in this case, resistance is proportional to the length. And here's the length. It depends on tau phi. So we need to solve this equation. That's what we have. And if I look back, it is characteristics for subohmic regime. So sooner or later, at sufficiently low temperatures, that will become comparable with T itself, and then something terrible will happen. It's not yet experimentally relevant, so I rather don't tell you about this part, but there is at least manifestation of subohmic regime. Okay, into the resistance doesn't depend on temperature, and we have a formula which is ohmic. For 3D, we have some strange expressions, so one has to really look into details. And actually, one finds 1 over T, which is proportional to temperature with some higher power, so it's all okay. It's a super-ohmic regime. So kind of coherence is easily preserved in three-dimensional materials. And there is a chance to lose it in one-dimensional. I shouldn't have said material. It is all geometry of your sample. Fine, that was a story about Nyquist noise. So let me talk about experiments. That's one of the classical experiments in the field, which resolved some problems of your experiments. First of all, what is the setup? Setup is actually very simple. They have a very long, I guess about 1 millimeter long, silver wire. Here's the wire. Right. It, how shall I say, wiggles. It meanders. So in fact, it's very long. The decoherence lengths at temperatures they work can be also pretty long. So it's about 40 microns in this case. You could see such scales even without microscope, perhaps. Good. So what did they do? It's rather also kind of rather straightforward primitive measurement. They measure this magnetic resistance and they do it at different temperatures at different samples. What they see dips, and from the width of this dip, they can extract actual decoherence lengths, which depends on temperature. Here you have it at different temperatures. You see that the peak becomes narrow at smaller temperatures, indicating larger decoherence lenses. Okay, let us look at the data, what they have measured. So they plot phi versus temperature, and it's double log plot. So any power law will be straight line in this double log plot. Good. So what they see at some temperatures, as I promised, above 1K, they have phonons and pretty fast decoherence. And then there is a large region at which decoherence becomes smaller and smaller upon decreasing temperature, and Nyquist noise theory predicts. We've just arrived. It predicts this power law, and this is what they see. It seems like the end of the story. Not yet. There was a kind of the whole scandal or whatever controversy in the community because many people, upon making low temperature measurements, produce this data. What you see in this plot, decoherence saturates in the limit of zero temperature. At least what this is what the data suggests. But this is totally crazy, and it is in conflict with all which we know about quantum mechanics. What is a simple reasoning? Zero temperature quantum mechanical system must be in a ground state, in very good quantum mechanical state. There is no place for any phase change. It is in a single state. So that motivated people quite a lot. And this particular work I'm talking about actually produced an explanation for this effect. As you see, they have three different curves with very different saturation levels. And these curves differ by purity of the samples in use. And their explanation was eventually you have to be experimentalist to digest something like that. That this effect is due to small number of magnetic impurities which destroy spin coherence. Okay, if you go at yet smaller temperatures which are hardly accessible technically, this effect will also cancel, but at least they indicate when impurity spin is completely frozen and you cannot scatter at it anymore. So that explained the puzzle of that child. The same group also made, or almost the same group also made experiments on relaxation. How much time do I have? Oh, I have quite some time. Right. So the idea was to look at electronic distribution in the wire which is spread like this. They apply voltage to the wire, so this is a situation of quantum transport. It is something which we would expect to see where here at this transparency. Electronic distribution in the middle. How one could observe this distribution? It's not simple. One could what could let this electrons tunnel into the lid. But if transparency corresponding transparency doesn't depend on energy, you don't see anything in this distribution. There has to be some feature which gives energy dependence of the resistance of this probe. And they found it looking at the Coulomb blockade features. Okay, so for some measurements, they can really see the splitting of this peak, indicating two-step structure. Was first observation of the step structure in almost macroscopic sample of several micrometers long. Good, so that's been proved. And again, looking at concrete mechanisms, looking at concrete predictions, they have found that these nasty magnetic impurities can also become a sort of dissipation at sufficiently low temperatures. And eventually they can completely spoil this two-step picture by making it a featureless curve, right? And the difference between samples in use is just amount of impurities in silver. You know what 9 is? 2 nines, 99%, 1% of impurities. So 3 nines, they got 5 and 6 nines. They could compare. That producing metals is that pure, it's very expensive. So if I remember correctly, that material was like 2 orders of magnitude more expensive than 5-9 silver. But fortunately, they have grants to buy it. All right, that's it. I told you about relaxation and decoherence by concluding the course of quantum transport. I told you about effects which spoil quantum nature, and we had enough about effects which are specific to quantum mechanics. It was various. I hope you could. It was kind of entertaining for you. Quantum transport is still kind of active research area. It's needed in quantum applications and sometimes in condensed matter physics. Very good. Thank you for your attention. Perhaps I will see you on Tuesday.
On my calendar, by the way, it says it's like